Gu- Hi guys, how's it going? Good evening, Dr. Jung.
Hi, good evening.
That was
Okay,
a good assignment, very enjoyable.
thank you. Let's wait for just a few more minutes until 5 past 7. Then we start with the overfitting and underfitting problem and cross-validation concepts um, from the lecture that we didn't mention, and then we can get into the hand-on practice for using scikit-learn library to do the regression and classification task. Hey, I think it's time to start. Uh, so we during the lecture session, we didn't talk about the overfitting and underfitting problem. This problem is a very common problems that we will face during our model training and testing. So it is a common problem. And uh, let's look at this problem through a polynomial regression fitting task. So what is polynomial regression? So it is similar to the linear regression task, but the difference is for linear regression task, we are looking for a straight line to fit and going through all the data points to represent the trend of the data, and the straight line is our model. But for polynomial regression, we are not looking for the straight line. We are looking for curve, a polynomial curve. We are using a polynomial curve to fit the data and let the curve to represent the trend of the data or the distribution of the data. And this polynomial curve will be our model in polynomial regression task. And so let's look at the input and output of the polynomial model. So the input are scalar values. So they are just single values because we can see from this R. So because it is just R, not R to the power of D. So for each data sample, it only have one feature value. So that is X value. It is a single scalar. And for each data sample, it comes with a label that is the target we are going to predict from the label. It is also, the label are also scalar values. And the output of the model or the mapping function, this F should be our representing our model, and it should be a mapping between a scalar value to a scalar value. So it is mapping from input X to output Y. But how can we represent this fitting curve? So we are using this polynomial function.
How do you know which is the highest power that you need to worry about?
Yeah, that's a good question, and we will answer that as we proceed to hyperparameter tuning. Yeah, that's a good question. P or the highest level should be hyperparameter for this model. So let's continue. So this fx should be our model output. So it is computed from this linear combination between the weight vectors. So all these weight parameters, W0 to WP, and it is a linear combination of between the weighting parameters and the x terms. So the x terms are the x to the power of certain number. So it starts from x to the power of 0. So that is 1. So it is just ignored here in the first term. And then x to the power of 1, x to the power of 2, and so on until the x to the power of p. And these x terms will form our feature vector to the model. So the first step is we're going to define this feature map that will change the input scalar to a feature vector. So it will become a feature vector of p plus 1 elements. But all these p plus 1 elements are computed based on the single input scalar value x. And now we have feature vectors for each data sample, and it's time to prepare the input data to feed into the model. So we need to prepare this feature vector for each data sample and then construct them into a large matrix. So we will use this phi to represent this input matrix. So for this matrix, it should be have n row and p plus one column. So n row means for each row, it will contain the feature vector for each data sample. And the p plus one columns, that means for each data sample, there should be p plus one feature values in this feature vector. So corresponding this to this p plus one elements from one, or say from x to the power of zero, x to the power of one, and then to x to the power of p. So this p plus one is corresponding to this p plus one element. So now we have the input matrix, and we know that this W vector, so this W vector should be a column vector containing all the weighting parameters. That should W0, W1 until WP. So it also have P plus one elements. So it is a column vector. So we can do the uh, matrix multiplication. So matrix phi multiply this vector W. This will be this term will be the model prediction for all the uh, data samples, right? So this will generate, let's say, not using Y anymore. So let's say we're using F. So F1, F2 until Fn. So this will become a column vector containing, and each element of this column vector will represent the model prediction of the corresponding input scalar. So it is corresponding to this n input data samples. So we have n f value or n model predictions. And then this one, we calculate the difference between this f vector and y vector. So the y vector are the vector of this true labels. So what this term is doing, what this difference is doing is it is calculating the difference between the model prediction and uh, true value. And then we calculate the L2 norm for this difference, and that will become the total difference between the prediction and the true value, and we square it. So this will become our new loss function. So we will use the least square regression to minimize this loss function and to find the best or the optimal values for this W vector. So all the like framework is similar to the linear regression, and the only difference is how we construct this model. So the model equation is different, and the input is slightly different. It is accepting one single scalar values, but before feeding into the model, it transforms it into a feature vector. And the rest should be all similar to the linear regression task. So is it all right till now? Okay, so how would this model output look like? So for linear regression, the model or the regression regressor is a straight line. And but for polynomial regression, the fitting line will be curved. So here we can see this is a comparison between the true function and data samples. So let's just get familiar with this illustration first. So The green line or the green curve is the true function. So we are going to sample some data from this true function. And this blue line, that would be the model. It is representing the regression line for each model. So here are three situations. So if we set degree to 1, that is corresponding to p equals to 1. So when p equals to 1, our model becomes W0 plus W1 and x. So we don't have the term x squared or even x to the power of p because the maximum value for p is 1. So we can only have W0 plus W1 multiply x. So we are familiar with this one. This is just one-dimensional linear regressor, right? It is just representing a straight line fitting. So we can see that this blue line is just representing our regressor. So it is just a straight line. So if the training data or the data samples are distributed around this true function curve, and we are using this straight line to fit the data, we can see that it will be a underfitting problem, right? So most of the data samples for training are not lying on our regressor line. So it is kind of distributed either above the fitting line or under the fitting line. But this straight line cannot fully represent the trend or the distribution of these data samples. So we say this is an underfitting problem. The fitted model cannot represent the trend. It cannot discover the pattern of this data distribution. And let's look at the one on the right-hand side. So what if we have a very high degree, like we set very high value for p. Now it is now our model becomes say p equals 15. This is p equals to 1. So when p is equal to 15, our model becomes fx equals to w0, w1, w2, and w15. We are getting this very a more complicated polynomial curve. And with this curve with very high freedom about this shape, we can get this very squiggled lines to fit over the data samples. You can see that from this blue curve, you can see that the model can go through almost all the training data points with high precision. Like there are only just a few data points that stay outside or not lying on this squiggle curve. But this will result in overfitting problem. So what overfitting problem means is um, it performs well or show very good performance on the training data. But for new unseen data, let's say if we sample more data from the true function, let's say we sample one data from this location, and we sample a data from this location. And now if we try to predict these data samples from the model, what we have is this is our prediction. This is f, and this should be y. So you can see that there's a large difference between the predicted value and the true label value y. So this this will result in poor performance for unseen data prediction. So for overfitting problems, the model can perform very well on training data, but for unseen or new data in like real world or in later testing cases, the performance will be downgraded a lot. So that is the overfitting problem. So that would suggest us to choose appropriate values for the degree or the complexity for the models, so that we can avoid falling into either underfitting or overfitting problem. So what if we set the highest degree for this polynomial function to be 4, then our function will become 0, W1, W2, uh, this should be W4, x to the power of 4, will become this. And this at this time, the fitting curve is neither too complex nor too simple as the degree 15 and degree 1. And the complexity is moderate, and it can like uh, going through or representing the distributed the data sample distributions without too many variations. And even when we are sampling more data from the true function, let's say we sample some data from these locations, we can see that the model prediction and the true data values will be very similar. So in this case, we can achieve both good performance on training and testing. So this is um, illustration or intuition for underfitting and overfitting problems. So is there any questions? So just feel free to unmute yourself and ask directly.
Hey, Doctor. I just I don't know if this makes sense. I'm still learning this stuff this week. So if you were to have a model with say 15 variables and you wanted to, and that's obviously overfitted, would you just reduce the degree of the power of P to create a curve that's similar, or what would you do to
So
fix that problem of overfitting?
like yeah,
Or you use less variables, or you use less what do you call it? Yeah, you know what I'm talking about. Yeah.
so it is a little bit this degree is not representing the variables. Like variables, I would say if we are using variables, we mean they are not correlated or they are independent variables or independent input. But for this polynomial regression case, all these elements in these feature vectors are all computed based on the single scalars, so that they are related. They are not independent variables. So if we can use this P to control the complexity of the curve, but if the problem is um, related to variables, I think that problem is more related to if specific variables have contribution or has um, underlying relationship with the target we want to predict. So it is kind of like uh, feature engineering problems or the feature selection problems instead of the optimization of hyperparameter P. So
Yeah, I found when I did feature to feature correlation and feature to target correlation, I could get rid of a couple of rows because a couple of columns because they had very little contribution, and some other columns because they were very closely correlated with other columns. That made the
Yes,
problem a lot simpler and a lot faster.
yes. In that case, if two or multiple variables are collinear, let's say, like the third variable can be computed based on the first and two, uh, first and second variables, we can just safely ignore the third variables because introducing the third variables may just share the weight of the first and second and make the model less stable, less reliable, and it will make the interpretation for those weighting parameters less meaningful. So yes, before we are going to train the model, we need to do some feature engineering, like reduce the uh, like remove the duplicated features. Maybe we may also remove the high correlated features to reduce this collinearity problems. So yeah,
Yeah, your suggestion in the assignment to do that turned out pretty interesting.
yeah, but for this one, it is more related to hyperparameter tuning instead
So,
of
so do we
feature
start with a
selection.
lot of a high degree and reduces, or do we start with a low degree and add and increase the degree?
Uh, I would prefer start from the simplest model and progressively to increase the complexity because for um, simple model, it won't cost that much time to do the fitting, right? So we can progressively spend more time to try a more and more complex model to find the degree four instead of just decrease like start from a very complex model because it may like say take days to just training the degree 15 and it may spend like hours to do the 14 and maybe a few another more hours to do the degree 13. It took a lot of time much more time to start from the complex and then downgrade the
Oh, of
complexity to
course,
the
that makes
appropriate one.
sense.
Yeah.
I have a
So
follow-up question. Would starting with something like a Taylor series, because of its implicit scaling, make this more responsive to tuning?
sorry, what's the question?
Would starting with a Taylor series or another polynomial, a special polynomial, make this fitting a lot more efficient?
Um, for this one, it is just an example, like one of the it depends on.
It's okay.
It
I'll
should
take
be
it
it
offline.
should be all right. The complexity, the difficulty for optimization should be at the same level because if we don't increase the number of variable, because if the input is only just one scalar value, if we calculate the gradient, we only calculate the the loss function with respect to this single variable. So we only calculate just one derivative, and this derivative will get our optimization to find the optimal weight values. Even we have like p plus one weight values, but for gradient calculations, we only we only need to do like let's say one derivative should be fine. So I would say the complexity at the same level. Um, but if the model involves like multiple variables, then the complexity for optimization will be increased. But the complexity for the model, I would say the model shapes will be another story. So there are like
Thanks for the explanation, Doctor. I think I'm just getting a bit confused because I've just sort of only spent one day on the work now. So yeah, I'll appreciate the explanation. The variables and the features are separate
Yeah.
problems. Yeah, basically from that, that's what I've gathered. And with the polynomial regression, was that in the LMS?
Polynomial regression.
Yeah,
Um,
for module two, because I don't remember reading about it. I'm just seeing it here.
it's
Maybe
it's
I'm
on the
reading.
slides. It's on the lecture slides. I'm not sure if on the page contents. Um, yeah, but the purpose for this polynomial regression is to let you know that we can also use a curve fitting, and the curve can have different complexity, and we need to choose an appropriate level for this complexity. But how can we do that is we are going to do that through cross-validation, and that's the contents we will talk about in a few slides later. The focus will be on the cross-validation, not on the polynomial regression, because there is not much complexity increase for linear regression. We need to use this polynomial regression as an example to introduce cross validation schema. Okay. So now we know
I'm
that.
sorry, doctor. Sorry. I
Yeah.
have a follow-up question on the same on the polynomial regression. Initially, if you go, could you go please go back to the previous slide? Your feature map has a p number of features, and and let's say it's 15. But you mentioned that you would start with the smallest model possible, simplest model possible. Probably this is what you're going to explain, but I'm just double checking. So given that you are starting with the simplest model, you will be picking some of the features, not all of them, for your first uh, training cycle, I would assume. Is that how you would go about it, and like maybe do a correlation analysis or dimension reduction prior to the model training?
Uh, this is a one-dimensional example. So that means you don't treat this feature vector as like p plus one variables. So they are all coming from one scalar values. So don't treat them as it is not like the house price prediction. So each element is representing an independent variable like the area or the number of bedroom. It is slightly different. Um, so here, when choosing different complexity level or say different p values, that means we will have different uh, lengths for these terms, polynomial terms. So then we will have different number of elements in this feature vector. Um, it's not about how we select the features. We are just you just treat this p value as
Okay,
parameter
right.
that
Yeah,
can
that's the part I
change the
missed. Yeah,
complexity of the curve. So
right.
if P is very large, we will have very squiggle curve. If P is small, the curve is more smoother. If P is 1, it will be downgraded to a straight line. So
Right.
yeah,
I got so basically so that's probably what I missed, and I think Alan asked the same question. So this is this vector is related to one feature, not that it's multiple features. It's related to the same feature.
yeah, that's true. That's true.
Yeah. Even in that case, like how would you reduce the this vector, because it's a one feature you have given? Like how would you do that? Is that the next part basically? Like
Yeah,
I'm not
that would be the next part. Like, how can we choose the appropriate value for P, right?
Right. And
Yeah.
just a quick last follow-up. Can we use the polynomial regression for multiple features as well, or wouldn't that will not work?
You can. The difference, it is like a linear regression. Like for linear regression, you can use multiple variables. Let me find.
Yeah, and the same way we could do it for polynomial as well, right? In case that it's not a linear regression.
Yeah, of course, we can do the polynomial regression with multiple variables, and then this equation will be rely on like more variables, like
More variables.
x
Yeah.
and y and z, whatever. So the equation will be different, but yeah.
Yeah. Thank you so much for this question. Thanks.
Okay, so let's continue. So now our problem is how can we choose an appropriate value for this p, or for the complexity of the model, so that we will not be able to trap in this overfitting or underfitting problems. So it's time to find a method to choose p value. And straightforward way to do that is, what about we just try different p-values? We can try degree 1, degree 4, 15, 30, and we use try and errors. We train models with different degrees and to evaluate their performance, and to see which model can perform best on testing data, right? We can use this way. So we kind of use like trial and error scheme. So this is the normal train and testing workflow. So we train the model based on the input vectors and provide their associated labels, and we got the model trained in these training phases. And then for testing phases, we will feed unseen data, and they will also come in the same dimension as the training input. So if we train the model using a feature vector with D elements, the new data will also come in D elements as the feature vectors. So in testing phases, we provide unseen data or new data to the model, and the model will predict the new data's label. This should be output. This should be output. It will generate the prediction. The model will generate the prediction with respect to the unseen input feature vector. So that is the normal training and testing phases. So we have seen that this is underfitting, and this is overfitting. So both cases a bad model, and we are expecting to find the appropriate level for the model complexity. So how can we find or how can we know if certain if certain situation is overfitting or underfitting? So we can observe it through the disparity between training and testing performance. So for training phases, we have loss function, right? We are using optimization method to keep tuning the weight parameters so that we can keep decreasing the value of our loss function. And the value of the loss function would be the error for the training. So if we train multiple models with different complexity, and let's say this should be the axis should represent P, and we can start from P equals to 1, 2, maybe 3, 4, and this is 15. And we can draw this line. We can draw this trend. So this is the lowest or the minimum loss function value when p equals to 1. So it is representing the error of these cases. And then we increase the model complexity. We try to train another model by setting p equals to 2, and we can get another error or loss function value. And we keep increasing the model complexity, and we train many models with different p values. And for each newly trained model, we can get their corresponding minimum loss function value, right? So we can draw this kind of curve, this curve to represent how the error of training would change while the model complexity increase. So it is showing this trend, right? It is showing the trend in showing in these three cases. So when the degree is low, the error for training will be high because these training samples, this training data are not lying on the straight line at all. There are some large variations between the model prediction and the data sample true values. But when we increase the p-value or the degree to a high level, we can see so let's say this will be high error. And when the model using high p-value 15, we can see that this time the model can almost go through all the training data points. So that means the difference between the training data label and the model prediction is very low, and that will result in a very low loss function value. So that also means we will have very low error, right? And this will be like moderate, say moderate error. And this curve line of training are perfectly showing this trend, and can show these changes of training errors change along while the model complexity increase. At the same time, we will also evaluate the model performance on a separate testing dataset. The data in this testing dataset will not be seen would not be seen in the training phase. So they are new data, they are unseen data. And we are going to evaluate the model of different complexity level on the same testing dataset to see how their performance changed while the model complexity increased. And we will observe that let's say this error would be just we will use it should be the mean squared error. So that means the mean difference between the model prediction and the true data values. We will observe this kind of trend represented by this green curve. So initially, for low complexity model, it will achieve very high error because, as this one suggests, so if we sample more new data from the true function, because the model is underfitting and it cannot predict the value properly, so it will still have very high testing error. But when the model complexity increased, we can achieve better fitting to the true functions. And for the new sampled unseen data, those errors will be decreased. So we will see a trend that the testing error would decrease while the model will decrease while the model complexity increased. But over a certain point, if we keep increasing the model complexity, we will get more too complicated curves that will overfit the data samples, the training data. So it is like the model is memorizing all the data distribution instead of figure out the pattern in this data distributions. So the model would start overfitting to the training sample instead of trying to figure out the trend of the data distribution. So if we keep increasing the model complexity, we will find that the testing error will start increasing instead of keep decreasing as in the early stages, right? And we will see this discrepancy at this turning point. So before this turning point, if we keep increasing the model complexity, both the testing error and the training error keep decreasing. But after this turning point, if we still keep increasing the model complexity, the testing error will start increasing, and the training errors will become lower and lower. If we observe such discrepancy between the testing and training phase, that means we are getting over the turning point. And this turning point would suggest this model complexity would be the best model or the appropriate complexity for our model training. So is it clear? Any question? This is an important illustration, or you better get this kind of illustration as an intuition, because later on when you do the model training, and also when you compare different candidates of models, it will help you to make a decision. Like if you need to keep the training process, or if you can stop the training and use the current model as the best selected model. So it will help you to make decision at the training phase. Any questions? All good?
Sorry, a question to understand a quick thing. So let's assume we had like 6 data points in the feature vector. So if we go about like the P maybe 3, what happened to the other like extra 3 data points? Are we taking it as like P0 value, or how would the final formula would look like?
Sorry, I don't get the.
So let's say the feature vector.
Continue.
The feature vector has 6 data points. Let's assume.
Okay, so let's see. Just for your example, so if we have, let's say not saying 6. Let's say we have in total 10 data samples, and so we use, let's say, 8 of them as the training. Use them for training, and we keep 2 of them as testing. So this is testing, and this is for training. And then we use these 8 data samples for training, and we will get the average error for this 8 data samples, right? We make prediction for each data point, and we calculate the main, let's say, the average difference between the prediction and the true value for these 8 data samples. And this will be a single point on this purple curve. And then the same model will be used to evaluate on this testing data set. We use the same model to predict the outcome from these two data samples, and we calculate the average of these two prediction between the average of the difference between the prediction and the true values for these two cases. And this average error will become a data point on this green curve. And now, we already got these two data points, and then we just keep increasing the model complexity and retrain the more complex model using the 8 data samples, and we draw the next data point and draw the next data point for the testing error curve, and then just keep going to fully draw this two curve. And after we fully draw this two curve, we can figure out where is the turning point. This turning point have an associate model complexity level, or it should be represented by a certain like p-value. It can be like p equals to 4, and then that's the optimal p-value we need to use. So, yeah, that would be the
Yes.
process.
Yes, doctor. That part I'm okay with. I'm just trying to connect the last discussion we had to the polynomial regression model. So
Yeah.
it like in the train set, if you take an example, just a one item in the train set is not a scalar, it's a vector. It has like multiple data points. As per the previous example we discussed about, like a feature map is consist of many data points for one example.
I don't get the question. What do you mean?
So in the polynomial regression example that we just witnessed, that it has the feature map is consist of number of like maybe n number of so yeah, so x to the power 2, x to the power 3, x to the power p, and this is a one example, right? We are talking about it. One example would have multiple data
So,
points.
yeah, so for one data sample, it will have one, let's say, scalar value as the input, and this data sample will then have one feature vector, and all these values are calculated from this x1. So we will have, so finally we want to construct this phi matrix. So finally we will have 1 x1 x1 to the square.
I got that.
And so
I just
and
misread it.
yeah, and this is xn square and xn p, like that. So we want to construct this phi matrix and multiply the weight vector.
Yeah. Thank you, doctor. Yeah, I misread something. That's why I got confused. Thank you.
Okay.
So that I'm guessing you're okay. So we got the training and the test, and obviously the best point is obviously at the smallest amount of test error.
Yes.
The other thing I'm missing something here, and that's probably trying to figure out. I'm guessing it's also dependent on how you split the training and test as well. So if it's 70-30, 80-20, 90-10, that's going to affect that as well.
Yes, it will. Like firstly, it affects the precision of testing error. Like if you don't have that much testing cases, the testing error will be the precision of testing error cannot represent correctly. And another thing is if you use if you reserve many cases as testing cases, you may not have enough training data to train the model. So that will be the
Yeah.
trade-off.
Is
So
there a
we need
curve that we have to also then plot out to show the split? So at 70 training, 30 test, there's another curve somewhere where it shows you the minimum error is used at say 78% training. If you do
but
more training, the error is worse. If you do less training, the error is worse.
Normally we don't do that. Normally we don't treat such kind of splitting as hyperparameter. Just sometimes we have a if you have more experience, like normally conventionally, normally we use like 70-30, or 80-20, or 90-10, as not normally used as the split between the training and testing. It depends on how much data you have. But the bottom line is we at least we need to keep enough data to train the model. So but
There's no
we are not going to
analytical way of
try like different split
there's
strategy.
no analytical way because all this is obviously all analytical and stuff. Analytical way to actually calculate the best for that particular solving that particular problem to work out the best split 70-30 to 90-10 somewhere in between. I guess you just try it and you go, I want to try 70, and if it's not, you're not happy with that, go to 80 or go to 75 and try that, and you're happy and not happy enough, go 80. It's getting worse, so you go back to 75 or something. Is that what you normally do, or that's
No, 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 we don't do that. Normally, we just simply said, we will just use 80 or 20. We are not going to like adjust slightly. Like if it works well, if we just use 81% or 82%, we are not going to adjust
I guess it gets very
splitting
expensive. Yeah,
strategy.
if you're
Yeah,
spending
we
a
just
lot of time to train and it takes days and days and days, and you go, no, I'm not happy with that, and you do it again, it'll be another days and days and days, and yeah, so
Yes. So normally we don't adjust the splitting strategy. The purpose for this splitting strategy is to just have two set of data. One set is used for training and one set is used for testing. That's the only
yeah,
purpose.
yeah,
Yeah.
yeah. I know that. That's been hammered home. But trying to figure out what's the best split, just choose something and stick with it. 70-30,
It
25,
depends.
25.
It depends on the depends on the entire data set. Um, Sometimes, like
Let's
let's
say you've
say
got
if
like
for
a
100
million
data
rows, a
samples,
million.
I may even prefer 90 and 10 because I need to make sure the
Yeah,
model can have
I
enough
think
data for
I think I'm
training.
getting the
Yeah.
gist of it. If you have like, let's say, 1,000 rows, you probably want to, not go 90-10. But if you've got a million rows, you can probably afford to go 90-10.
Um, yeah, but typically, like 70 or 80 will be preserved as for the training.
Yeah.
But yeah, if the data set is
I
very
guess
small,
what I'm trying to get at is
yeah,
probably trying to hint towards the justification of choosing the split in
But
some.
then
Yeah.
remember that if you're using cross-validation, you don't have to reserve a validation set like we did in deep learning.
yeah. For deep learning, normally we don't do cross validation because that that is time consuming. Like if you train a very deep learning model, it may take like days, weeks, or even months. And if let's say if we do
Yeah,
the
it's
fivefold, the
expensive.
time will be like five times of the
Yeah,
single round, and
yeah,
we
Thank you.
cannot wait.
yeah. I guess I'm asking because if I need to justify it in something I need to hand in and say I chose this split, I don't have to spend too much time justifying it.
Yeah, for the consideration of this training and testing split percentage, you only need to consider if you have enough data for training,
Yep.
if the testing case or the number of testing case would enough to reflect the precision of your evaluation measure. Let's say for classification task, if you only preserve like 10 cases for testing, um, then the classification accuracy may not achieve like 90,
Yeah, that's what I
95
was
or
saying before. Like
99% if
in a
you just
CS,
make
let's just say a
single
CSV
inspect.
file that has, 1,000 rows versus a CSV file that has 1,000,000 rows. You can
Yeah,
afford to go 10%
yeah,
for testing on a bigger one. Yeah,
yeah, that's true.
understood. Oh,
Okay.
thank you.
Um, Now, this is the basic idea about the training and testing. So we know that we can figure out the hyperparameter P through this training and testing explanation, and then observe the discrepancy between these two errors. Let's just have 5 minutes break, and we continue to look at the cross validation. So let's come back at 8:06.
Doctor, can I ask you a question?
Yeah.
I have done the submission. I submitted the uh, today, and I see the submission screen, the .ipynb, ipynb. This file has not been submitted to Turnitin because the file format is not supported. Is that a problem?
That's all right. That's all right.
That's all right.
Yeah,
Okay.
as long as the Turnitin can scan your report, it's fine.
Yeah.
And it doesn't matter if the Turnitin scan your notebook file or not. It doesn't matter.
All right. Okay. All right. Thank you.
Okay, let's continue. So we have seen that we can use the training set and testing set to generate these errors between the prediction and the true value. And then so we can try different model complexity. We can set different numbers and train different models corresponding to this each complexity level. And for each model, we will have a score corresponding to the representing the performance of the specific model on the same testing set. So with this testing performance or testing errors number collected, we can find the lowest error among them. And then the corresponding model that generates this lowest error would be the best model. And the complexity or the hyperparameter value for this model would be the optimal value for the hyperparameter. So this is the most basic approach to do that, but there is some drawback for this approach. You may observe that this is just one-time testing, and it highly depends on the split of training and testing data. So maybe accidentally we just preserve a very simple testing data set. So just by accident or by luck, and then this testing data set, let's say specific model, just works very well on this easy testing data set. So it will not be fair to other models in comparison. So how can we leverage this problem is we can use the cross validations. So to make the situation fair, we further split the training data set into training samples and validation samples. So previously, all these data samples are regarded as training samples, and this would be the testing data set. So we don't want to do this one-time testing or evaluation. So we want to introduce one more evaluation phase so that we can be more confident about the trained model. So we further split the previous training dataset into training data samples and validation samples. So we just call this time we just call this training dataset and validation dataset. So this would be validation dataset. And now we have three datasets in this case. So the purpose is we want to find the optimal hyperparameter value. In polynomial regression case, we want to find the optimal p-value using just the training and validation dataset. So after we find the optimal p-value, we are going to use the testing dataset to just report the final performance of the optimal model with the optimal hyperparameter values. So now this time, the testing dataset will not be used to evaluate all the model. It is only used to evaluate the performance of the best model. So just for reporting purpose. Because after we train the model, we need to report the model performance to the public, right? So if I train the model and I'm proud of it, and and I want to convince others that my model is good. So I need to give a performance measure, and this testing dataset will be used to report such measure. It is like the final exam score. But how can we find the optimal p-value is through the training and validation dataset. So we can do whatever we want with this training set, training and validation dataset to find out the optimal p-value. But we will not involve this testing dataset until the very end reporting phase. So in this case, we are not using the testing dataset to generate those error curve or error score. So we are using the validation set to generate those error score. And we still going to try different p-values, and for each p-value, which we train a different model, and we need to generate the validation score for each trained model, and then compare the error. The model with lowest validation error will be the best model, and the corresponding p-value will be the optimal hyperparameter value. And this approach is still like near one-time evaluation, right? We may still by luck just find a easy validation dataset that is unfair on the other models. So we can further alleviate this problem by introducing the k-fold cross validations. So what k-fold cross validation do is we split the entire training data into a few folds of, let's say, into k parts. And we are going to do this train and validation phase or evaluation k times. And for each time, we are going to use different part for validation, and the rest of part will be used for training. So let's say for 5-fold cross validation, that means we are going to first split the entire training dataset into 5 parts. And in the first round, we are using the last part as the validation. So this is not testing, it is validation. So that will be more accurate terminology. So we are going to use the last part, the 5th part, as the validation, and all the other 4 parts will be used for training. And in next round, we're using the 4th part as the validation, and then the other 4 parts used for training. And so in this way, after 5 rounds, we will use all the 5 parts have been used for validation at least once, right? Exactly once. So in this way, we can fully utilize all the training data samples or training data sets to evaluate the performance of the model while setting different complexity level or using different hyperparameter values. So after the 5 round, we calculate the average of the errors on each part validation. and the average error will be the validation error. And for each hyperparameter value, it will have one average validation error. And now we are not comparing this one-time validation error. We are comparing the average validation error from each K4 cross-validation. And the smallest validation errors will show or help us to choose the proper hyperparameter value for P. So that is the procedure for doing K4 cross-validation. So let's say for tenfold cross-validation, that means for the training data set, we are going to split it into 10 parts or 10 folds. And for each iteration, we are going to use one part as the validation. This is validation. So that we don't confuse it with the testing data set. So this is validation fold. So we use one part as the validation fold for each iteration. And then in next iteration, we change to use another part as the validation set and the rest of the fold as the training data set. And for each iteration, we will have a validation error. So after 10 iteration, we will get 10 validation errors, and we calculate the average of this validation error, and we just call this average validation error. So this validation error is for one specific p-value. It is maybe for p equals to 1. So it has one average validation error. And then we increase the model complexity to p equals to 2, and we do this tenfold cross-validation again, and we will get another average validation error. And we keep doing this for all the other complexity level. So that means after, if we want to test 8 different complexity levels, we will have like 10 average validation error, and then we are not compare this single validation error. We are compared 10 average validation error, and then find out the lowest the model with lowest average validation error. So that is how we are using the cross validation or K-fold cross validation method to get a more fair evaluation or selection for the hyperparameter value. So for summary, the polynomial regression we have looked at the polynomial regression for nonlinear problems. Nonlinear problems means those data distribution are not lying on a straight line. They cannot be best fitted by a straight line, and they are showing a non-linear or curved trend. And polynomial regression has a hyperparameter P, and for hyperparameter, these parameter values cannot be optimized by optimization method like gradient descent method we learned in last week. So not last week, in the lecture session. Because this hyperparameter cannot be optimized by gradient descent method, we need to use the cross-validation to find the optimal value for these parameter values. And these hyperparameter values, like inappropriate hyperparameter values can result in underfitting or overfitting problems. And both we are not we cannot get good models if we are trapped in these two cases. So for the polynomial regression model, very small p-value will result in underfitting, and very big p-value will result in overfitting problems. And we can tune or find the optimal p-value through cross-validation. And hyperparameters are determined before we start to train the model. So it is decided beforehand, or it is set before the training, instead of tuning during the training phase. And we need to make sure that the model parameters and hyperparameters are independent of testing data. So testing data should be preserved until the very end of the phases. And we only use the trained model. We only touch it when we are going to report the final model performance. Okay?
A quick question here. So the polynomial regression we've been talking about tonight, is that the same as the polynomial kernel?
They are sharing a similar equation, but used for different purpose. So the polynomial kernel is used to like introduce an extra dimension to the data samples so that it can make the data separable. But this polynomial regression is using the polynomial function or this kind of equation as the model. It uses this equations as the equation to generate the output. So the equation similar, but the purpose are different.
Right. So the codes will be different.
Yeah.
Okay, thanks.
Okay, if no more questions, we will let's get into the lab notebook. Let me find it. Okay, can you see the part 1 regression notebook?
Yep.
Okay, great. So in this lab, we are going to go through the regression task using the scikit-learn library. So here we are going to working on this car price prediction task. So because our target is the selling price of the car, it is a continuous valued variable. So this would be a regression task. So
Doctor, can you put the link into the chat?
sorry,
Can you put the link into the chat
what link?
to the notebook?
This is my like
It's your first one.
collab location. So yeah, you can download. Let me find it. You can download the notebook from the LMS and upload to your own collabs.
I'll just share the LMS page with the. I think it's a live recording. That's where it is. All the solutions are there too.
Okay, thank you.
Let me see. You go to module 2 and scroll down to the live sessions of module 2. And then here are the lab notebooks. And you right click and save link as to download this lab notebook and upload it to your Google Colab workspace to work on. And here, the data set, you need to upload it as well so that the Google Colab can read it. Okay, and here's a summary for the data set. So it has 12 columns and car names, years, selling price, and so on, and along with its short description. I'm not going to go through that. So all this data are saved in the car details. So by the way, I think I need to connect to a runtime so that okay. So to upload the dataset to your Google Colab, one way to do that is you can just drag the CSV file to the folder or to this files tab, and you can see that this CSV file has been loaded to your workspace. And now, so if you are going to read the CSV file by using this, by just providing the name, it will be able to read the uploaded CSV file. And another way is you can upload the data into your Google Drive and then mount your Google Drive to the workspace, so that in that way you will be able to persistently save the data. Because if you just disconnect it from this runtime, those data are not saved in your Google Drive will be lost. So it will be refreshed every time you connect to the Google Cloud runtime. So just for your information. So if you are going to, so when you do your assignment, if or later on if you are working on your own project, so if you want to save your data, there may be some important data or intermediate data that is important. Make sure you save it to your mounted Google Drive so that all this data will not be lost in the next time when you refresh the Google Colab runtime. Okay. Anyway, to read the CSV file, we are going to use the pandas library, and we first import it as PD, and we call the pd.read CSV file to read the information in this CSV file into a data frame. So data frame is just a data type of pandas. It will store the data in this table-like organization. So we give the variable the data frame name as dataset. And now we can get the length of the dataset by calling len and providing dataset as parameter. So it will show 7,761. So that is the total number of the rows in this table. And we can print the first 5 records in the table by using the head method. Of course, you can print more. You can supply like different numbers in the parameter. Let's say first 10 by providing 10. But here we just want to have a quick look about what information are stored in the original table. So we have all these columns names, like name, year. It has been already specified as a beginning description. And we can see what kind of value stored in this in each columns. So under name, there are just the car model name. Years, there are some numbers. Selling price are numbers, and kilometer driven, the numbers, fuel, cellular type, transmission, they look like they are storing string in this column. And for mileage, it is a combination of numbers and string that is representing the unit and so on. So after observing the data, we kind of know know some procedures that we need to perform. Let's say for this fuel cellular type transmissions, and they are categorical data, so they are not numerical data. So for this case, we need to let's first talk about the numerical data. So let me share the screen. Okay. So you can find this slides on the live sessions page. It is in PDF. So for categorical data, there are two types of categorical data. So one is ordinal data and one is nominal data. So what is nominal data? So nominal data divides variable into mutually exclusive labeled categories. A few examples would be like eye color, could be blue, brown, green, or smartphones can be from different brand like iPhone, Samsung, Moto, and transport, as a bus, train, car, and so the characteristic of nominal data is they are representing different category, of course, and they don't process like intrinsic orders between this within their different values. So they don't preserve any orders in this among these categories. So we cannot say like blue color eye is superior to brown or green eyes. So there's no such relationship among the nominal data. In comparison, for ordinal data, so these variables have a natural order or rank. So examples for this ordinal data are school grades, like we have grade A, B, C, education level, like bachelor, master, PhDs, like seniority level, junior, mid, senior. So these categorical values have orders, intrinsic orders among them, right? So we know that grade A must have like higher score than the grade B. So they come in order. So then with this different, considering this difference, we need to have different processing method for them. So for nominal variables or nominal data, because they don't have orders, so we are going to use the one-hot encoding. So what is one-hot encoding is before processing, all the candidate value are stored in a single column. So there's a color column, and for each entry, it can be red, green, or blue, representing the eye color. But after one hot encoding, it will become three. It will be converted to like 3 GB. It will be converted to three separate columns, and each column is a binary columns, and it is using the either 1 or 0 to represent the information in previous before processing. So D1 is representing the color for R of color for red. So that means if the cell has value 1, that means originally this record should has a red color eye. If it's 0, that means this record doesn't have a red color eye, and so on. So we can see that for originally, if it is green, it will set the cell in green column as 1, and the other 2 cells are all zeros. So this is one hot encoding. And since these 3 columns are linearly related, we can use the dummy encoding. So the difference between one hot encoding and dummy encoding is it's just get rid of just one column from the converted new columns.
Doctor, can we use true and false instead of 0 and 1?
Yes,
True,
it is
false.
just a representation for binary information. In pandas, it is using true and false. Okay.
Okay, yeah, thank you.
I have a question because it decrease 1, then become D1, D2. Can it become D2, D3, or D1, D3?
Yes, it is like theoretically, you can do that. But if you are using the method, we will look at how we can do that in using the pandas. The built-in method from pandas will just remove the last columns. So they're equivalent. So you can remove any one of them and it will not affect the final result.
Okay, thank you.
Yeah. Okay, that would be the difference processing that we need to follow when we seeing like different type of categorical data. So for nominal data, we need to know that we need to use one hot encoding or dummy encoding to convert the columns to these binary columns. But for ordinal data, it is straightforward. So we can just use integers to represent their orders. Let's say we can use 0 to represent C, 1 to represent B, and 2 to represent A, so that after conversion, the converted integer can still preserve the natural order of this ordinal data. So we just using integer values to replace the original string value in this ordinal data. Okay, let's get back to the notebook. Okay, so we can observe that we have like field type, cellular type, transmission, and owner, and this should be categorical data, right? And field, cellular type, transmission seems more like nominal data because like fuel type can be diesel or petrol. There should be no orders among them. Transmission can be like manual. There is automatic and there are different transmission type, and we can say automatic type is superior than manual type or vice versa. So there is no order. So fuel cellular type transmission should be nominal type, but for owner, first owner, second owner, third owner, there it seems that it is holding some intrinsic orders among these values. So we may treat it as ordinal data. And for mileage, engine, max power, it is a mix of the value and the unit. So we only care about it seems that the unit are consistent. So we don't need to convert these values to considering this unit. We do care only about the values now. So we may need to do some processing to get rid of the units and only keep those values in the columns. So it suggests this data appearance suggests some pre-processing work for us. But before we get into those data conversion work, here are a few like common process we need to do, like the common data cleaning process to walk through. So we need to drop columns that we are going to use because the task is going to train a model to predict the selling price of the car. And after observation, we can see that the column name, it is holding different model name of the car. And it seems that each row is holding a distinct model name, and it is not useful for our prediction. Like we cannot like even we put this information feed this information into our model for fitting. When a new car comes, and if the car comes in like a new model or this model name, the model name is not contained in this training data, the model will still don't know like how to predict the price based on the given new name because these names are categorical data, and if the name is new and not contained in this training data set, it is not useful. So we don't need the car name or the model name columns. So we can drop the columns. So we can use the drop method, providing the column name, that is name, specifying the axis equals to 1. That means we are going to drop a column instead of dropping a row. And in place equals to true. That means we're going to update this data frame. So if we don't set the in place, this drop method will generate a new data frame and without touching the original data frame. And in that case, we need to assign it to a new variable. So in that case, we better just assign it to new variable. So in that case, dataset will not be touched. So the information will not be changed, and now data2 variable will holding the data frame without column, without the name column.
Just a quick question, right?
Yeah.
This is probably irrelevant to this example, but I guess if in future, if the name was a brand, the brand might affect the price, right? So a Mercedes versus a Hyundai.
Yeah, if there's a column brand that is
'cause I'm
more
looking at that going,
general,
oh, that's Honda, that's Hyundai, the Skoda.
yeah,
Obviously, this
in that
example,
case, it will be useful, and we can keep that brand column
yeah,
because this name column is just too detailed, and
yeah. So it's okay to put in the assumption we don't need the name.
yeah. Okay, and next step is okay. After dropping the name column, we print the data set again. We can see that now now the table doesn't have the name column anymore. It has been dropped. And the next step is to dealing with the missing values. So we need to identify if there's any missing values first. So we call it through the NA method. So NA is representing not available. So any values that is not available will be counted as true. And the sum function will count or summarize how many true values for residing in each columns. So in this way, we will get vector or an array summarizing how many missing value residing in each columns. We can see that there is no missing value for year column, selling price, but there are 19 missing values for mileage. That means there are 19 rows that have mileage, engine, max power, seats, those information missing. Since we have like more than 7,000 data, we don't care that much about these 19 losses, so we can just drop those 19 rows directly. So we use the drop NA method to drop the rows with missing value entirely. We drop the entire row, and we can see that after dropping the rows, the total number of rows becomes 7742. That is just 19 rows shorter than the original data set. Then we are going to check if there is any duplicated rows. So we can do it through calling the duplicated method and going to check if use any method to see if there is any duplications in the data set. And then the return value is true, and then we can call the drop duplicates function to do the actual dropping actions. And so after dropping the duplicated rows, we can see that the total number of rows has further decreased to more than 6,000. And now we can do some processing on the value stored in the specific cell. So the first one is we want to deal with the mileage, engine, and max power columns because we want to get rid of the unit string and only keeping the numeric values. So here we just define a function, and this function just receives the data frame and the column name, and for all the rows or for all the entries in this specific column, it is going to split the string by using the space separator. So that means, let's say for this example, for this engine 1248 cc, so here so in this for loop, I should be equals to 1214 cc. This is the string, and this split will result in a list of splitted string. So it will generate a list of two strings. The first will be 1248, and the second element will be CC. And we only care about the first numeric value, so we are going to access the first element, and that is the first 1248 string. So now this number variable will be holding only this 1248 string, and then we append it to a new list, and finally we return this list. So this list, after recalling this method on specific column, we will return a list of string, and each string is a numeric value for this engine. So if we are calling the remove unit function on the engine column. But first, we call it on mileage columns. And so it will remove the, let's see what mileage column have. So here for mileage column, it is 23.4 with KMPL, and it will just remove or only remove the unit and only keep the first numeric string, because now the columns only holding the numeric string. But what we want is the numeric values. So we need to convert the string to numeric values by using the toNumeric function to convert the data types. And so after this process, we can see that the mileage now only store the mileage values. And then we repeat this unit removal and data type conversion process for the engine and max power. And after the process, you can see that now these three columns are holding the numeric values. And here we don't like the year, so we want to convert it to some age feature. So we can calculate the age of the car. So here this year is 26. So we can just use 2026 and minus the year columns. And now
I don't think we should change it to 26 because the older the car is, that price will be wrong. So the age should really be representative of the age of.
Okay. Yeah. I mean, it could be changed. It could be changed. And this the age values will be stored as a new column called age. So we can create a new column for this data frame using this format. And then we can, because we have already converted calculate a new age column based on the year column. The year column's information is no longer useful, so we can safely drop this year columns. So now if we check the data frame, so we can see that now we have age column, but we don't have the first year column anymore. And we can get a summary of the numeric columns. So we can call it using describe. It will give us the count of the values, the mean of the values, standard deviation, minimum, max, and those values at certain percentile. It is just some basic statistic for each numeric columns. So we may have a first sense about the data distribution and may probably observe some potential errors. Maybe there's a car that has maximum age like 200, and it is less probably that there will be a car in this data set to be over 200 old. So we may figure out what's the problem of the data. Maybe we did something wrong. So it gave us just some basic statistics for each columns and help us to get familiar with data and observe some potential errors. And we can handle the categorical variables. And now it's time to deal with the nominal and ordinal variables. So here, the describe function only provides statistic for numeric values, but all the status for categorical columns are not included in this statistics. So we can see that there is no cellular type, field, transmission listed here in this described table. So we can, for the information about the categorical variables, we can use the value count. We can call the dataset, the specific column, and value count function. And it will return the count for each categorical values for specific column. We can see that for few column, it has over 3,000 diesel values, over 2,000 petrol, 51 CNG, 34 LPG. You may have a first understanding about the distribution of categorical values. And let's first deal with the ordinal variables. To deal with ordinal variables, we know that ordinal variables come in order. So like the owner column. So first owner, second owner, third owner. So we simply just replace the string with the integer that can represent this order. That will be fine. So we use 1 to replace first owner, use 2 to replace second owner, 3 to replace third owner. So we provide this dictionary. Recall that dictionary is a Python data type. So we provide this dictionary to the replace method of this owner column. So after this line, we assign it just back to the original columns to overwrite it. So now the owner column is not holding this text anymore. It is holding the integer values, right? 1 for first owner and 3 for third owner. That is how we deal with the ordinal variable. And for nominal variables, we use the getDummies function. So recall that we need to use one-hot encoding or dummy encoding to deal with the nominal variables. But both implementation in pandas are implemented in this single getDummies function. So if we let me see if I open the, so we can search for it. So if we read the documentation, so if we read the documentation, we can see here, drop first. So if we use the default value for this drop first parameter, so it will be one-hot encoding. So if we set this drop first to true, that means we will get k minus 1 dummies. That means it will just remove one converted binary columns from the result. So that will become the dummy encoding. So here we just simply use the one-hot encoding, so we don't specify the drop first parameter. We just keep the default values. So here we call getDummies. We provide the data frame. We specify these 3 columns need to be converted using the one-hot encoding, and we check the status after conversion. So we can see that the fill columns now becomes 4 new columns because there are 4 candidate values in this categorical values in these fill columns before conversion. So we need 4 new columns to represent this information. And inside each columns, it is setting true, meaning originally it is diesel or not, and like this. And for seller type, so it can be dealer or individual. So it only use, we can see that it
Sorry,
only
Doctor, if I may ask, here, as a statistic of the fuel, diesel, and petrol, isn't showing imbalance of data?
Sorry?
This one, the number of fuel and number of diesel and number of this one, it show imbalance in terms of number of car. does it like look like the system or the model going to bias toward like a specific type of car?
From the characteristic of the data set, yes, it is imbalanced. But depending on what kind of model you are going to use, it may not affect and how the model was trained, it may not affect the final result. Like even though you don't have that much like CNG or LPG fuel types for the fuel information, if the model like after the training, if the model figure out that like these two values are dominating the like prediction of car selling price, it may like allocate more weights on these two columns on this fuel LPG or fuel CNG columns. So whenever it saws like one or two on these columns, so it may like these two columns may contribute more in the prediction, in the price prediction. So it depends. Yes, from the data set point of view, it is imbalanced, but for the impact on prediction performance, we need to look more into the evaluation of the final model performance.
Is the imbalance the data more affect works having more impact when is doing the classification and then the imbalance data is in the feature? Oh, not feature,
Because it is a regression task, it is less in comparison with the classification task. It is less sensitive to those imbalanced data. Like think of a classification task. Like if you have more let's say we are classifying the dog and cat image. So if for training data, if there are more, like much more, like 90% of dog image than the cat image, the model may tend to generate dog image to achieve the high accuracy. But for regression task, it is generating the price values. It is more relying like the data distribution for this the data distribution will affect more on the regression performance. So it is less sensitive as classification task. But yes, generally speaking, imbalanced data will affect the regression, the model performance, but it's worth to take a deeper look after we train the model. Okay.
So I have the follow-up question. So I mean, I'm trying to ask if, let's say, if there are outliers, and if the target value is, let's say, price of the car, would you treat those outliers in this, or you will keep them?
It depends. It depends on what. It depends. Like some model are not sensitive to the outliers, like SVM, and for linear regression, it may be sensitive to some outliers. So we need to use different like from. So as we said, for SVM, only the supporting vector affecting the model performance, right? It will affect the position of the hyperplane. And if we remove data point that is not a supporting vector, it will not changing the hyperplane position. So we can know that the SVM is less sensitive to outlier. So it doesn't matter if we remove the outlier before training. If we need to remove it before training. So, and another thing is sometimes we don't really know if it is outlier beforehand. So sometimes maybe it is just a rare case and it's worth keeping it and put into as the training data because it is rare case and we don't have that much data, but it doesn't mean it is a outlier. So it depends. It depends on the situation.
Thank you.
Okay, where are we? Okay, so for nominal variables, we use getDummies functions to convert the single column of categorical data into like multiple binary columns. And we can get the shape of the data frame by calling the dataset.shape. And it will return a tuple with first element showing the row size, number of rows, and the second element showing the number of columns. And now it's time to get into our training process. So we need to prepare the data for training. So the first column now is the selling price. That is our target. So we want to preserve it as our prediction. So we just extract it and assign it to a variable y. And for the rest of the columns, these are the information we are going to use as a feature vector. So this is the matrix X that will multiply the weighting for linear regression. That this X will be the matrix that multiplies the weight vector and to generate the prediction for each input data. Okay, now we have training input X and true value or true label Y. And now it's time to do the split of data set. We need to split the data into training and testing. So here we just use the 90% for training and 10% for testing. So here we use the train test split function imported from the model selection of scikit-learn library, and we provide the X and Y, that is the training input and the label, and the test sign is 0.1, representing the 10% for testing purpose. So therefore, the code will automatically know that there will be 90% data kept for training. And we set a random state 1, 2, 3, so that for reproducibility. So next time when we will rerun the cell, we will generate the same split as this time. So so the return value of this split function will be 90% of X used as training purpose and 10% of X used as testing purpose, and 90% of training data, 90% of Y used for training label, and 10% of Y used for testing label. And now we need to apply the normalization on both training and testing data set. So why we need to do the normalization? Because we can see that the range of this input feature can range from, how much is it? Like can range from 145,000 and to this kind of 1 or 10. This is a large variation among this input. It will affect the interpretation of the weighting parameter values. So, and it will make the optimization less stable when we do the training. So we want to compress those values into a similar range, for example, between 0 and 1, so that all these columns can make equal contribution. Not can make equal contribution. They all have the opportunity to opportunity to make contribution. So we use the min-max scaler. This min-max scaler will comprise each column into the value range 0 and 1. So we use this scaler to fit to the training data. And so this fitting means it will calculate, or it will train, it will set the scaler to know how to transform each columns into 0 and 1. So there is underlying equation for that, but there are parameters for those, or constant or variables controlling those equations. So it needs to find the transformation values for those parameters. So this fit is going to set those values for the transformation. After knowing how to transform each column into the expected range, we use this scaler to transform the training data, the training input. And we also need to do the same transformation on the testing input. Because we cannot allow testing data information to be exposed to the training phase. So this min-max scaler must only fit based on the training data, and it cannot touch the testing data. It cannot fit. It must not fit to the testing data input.
That's a good point. I missed that. That's good. You split it and then you normalize. Okay.
Yeah, it must learn how to transform only based on the training input, and then but the learned transformation need to be applied to both training and testing input. So that's the point. And now we have got the data prepared, and it's time to do the actual training. So we first train the linear regression model. So we import it, and we create the default model, and we try to fit the model or fit the straight line by providing the normalized training input and provide the training target, so that the model know what is what's the expectation. It can, after this fit is going to do the actual fitting process or do the optimization process. And this score function is used to return the score, the performance score for the trained model. So we can provide the normalized test input and the label of testing data set, so for comparison, and the return score will be the R squared. So that is the coefficient of determination measure. So you may have known that from other courses or some statistic courses. So if this value is 1, that means the prediction is perfectly matching with the true labels. If the value is 0, that means the performance is similar to a model that always predicts the average values for the labels. If the R square value is negative, that means the model performance is even worse than a model that always predicts the mean values. So that means that is a very poor model. Okay, so now we can get that the performance score for this trained linear regression model is 0.59, so it is all right. And now we try to fit the support vector machine for regression. And again, we just create a default model. We just use the similar code to do the fitting with the normalized input and label, and we report the score. Now we can see that this time the R-square score is a negative value. That means this fitting is very poor. So how can we improve this fitting for the support vector machine? So the problems maybe we are not using the optimal hyperparameters that controlling the complexity for the support vector machine for regression. So it's time to use the cross validation to find the optimal hyperparameter values. So here we just use the k-fold, and it is using the tenfold cross validation because we set 10 for n split, and we shuffle the data, and we set a random state for reproducibility. So this k-fold was a definition for how we split the training data into 10 parts. Here is again, this is the default linear regression model, and we use the cross validation to do the training and let the cross validation to report the average validation score for us. So we need to provide the model we want to validate, and we provide the normalized training input. We provide the training label, and this is the cross validation strategy that is k-fold we define here. This is how we split the data and do the cross validation. And the result will be holding the cross validation result, and if it will show the 10 iteration of cross validation, right? Because it is tenfold cross validation. So we are doing this validation 10 times using different part of the tenfolds. And we can also get the average average validation score by using the mean method. So we can see that the average R-square is 0.63, and we can also observe each iteration's performance. And to do the cross-validation for SVR is similar, so we can also do this. And we can observe that the average validation score is still negative. And after observing the individual validation score, we can see that all these iterations achieve negative R-square. So that means it is not the problems of the split of training and testing data that resulting in this poor performance. It must be the problems or the complexity problems of this SVR. So we need to find the optimal hyperparameter for this SVR model. So it's time to use the grid search CV cross validation. That is grid search cross validation. So we need to set all the parameter value candidates that we want to search from. So let's say for linear regression, we want to find, should we set true or false for the fit intercept parameter? Should we set true or false for the positive parameter? So, and we are going to use the grid search CV function to find the optimal value or combination for this parameters values. And we are using this function. So grid search CV providing the parameter set and the cross validation strategy and we're going to feed with the normalized input and training labels, and we can get the best score out of this grid search. And the best score is 0.63. We will look into that later. And we can do the similar stuff for the SVR model. So for SVR model, we can set different values for the kernel, C, degree, coefficient F0, coefficient 0, gamma, and the detailed parameters settings. That is that we can use it. We can see from the official documentation. We can see the meaning of this controlling parameters. What is it used for? Some of the settings are only applicable to specific kernel. We can see that the degree is only applicable to when we set the kernel to polynomial, and it will be ignored by other kernels. So if we set a degree, but we are using like linear kernels, this degree setting will be ignored, and so that means if we are doing the grid search cross-validation with these settings, we would do many redundant fittings with these settings. So when you do your like home assignment, so you find out that it took too much time to do the cross-validation for grid search. You want to reduce the number of fit. So the first thing you need, I would suggest you to take a look is if there are many redundant search. If it is trying to search for some parameter values that is not taking effect. Okay. So again, we can get the best score.
Doctor, is it okay to reduce with max iteration, setting max iteration?
Max iterations. You can set the max iteration, but you need to
It was at the bottom. It was at the bottom.
Yeah, I can see the max iteration. The max iteration would be so for it will affect the fitting process. So it will affect how many iterations it will use to fit the model. But sometimes the models are not fully trained if you specify a max number of iteration. So choosing an appropriate number of max iteration may be another problem for you if you are like trying to explore different models with very large complexity divergence. Does it make sense? So maybe say 100 iteration will be enough for linear, but maybe it is just a start. It is a very early training stage for like sigmoid or polynomial. So you may not have set a like universally applicable maximum iterations for all kernel types. So that may be a problem. It depends. So if a model is less trained, like it's trained with less iteration, it may be the poor performance may be resulted from this insufficient training. So it will be not fair for those models. And reported score or selection of the optimal hyperparameters may be not what we are expecting. So the purpose is we want to find the best model, right?
Doctor,
Okay.
does that function pass when you pass the kernel? Does that just iterate through each kernel type and work out the best with that call function? So the grid search params, does it go through each parameter on
Yes,
the
yes,
default?
that's a good question. Yes, I can show you. I can that is what I want to show you. Just a second.
So scikit-learn would have default iteration set for each kernel, I guess. Then so when they expect it to converge, or
It is trying to it is going to try
yes,
different combination of these parameter values. So let's
yeah.
say it will try linear c equals to 1 and degree is 8, degree is 3 and coefficient 0.01 and gamma is auto. And then it try to, okay, I'm not using 1 anymore, I use 5, and then it will try all the combinations. So in total, so we have 4 candidates here, and 2, 3, 3, and 2. So in total, there are 4 times 2,
Times 2. No,
3,
it should be
or
2.
2. Yeah, 2.
With the
Sorry.
potential of say for example degree being a parameter that's not used in linear, for example.
Yeah.
So they will be ignored on that iteration, for example.
Yeah, that will be the like redundant because you're trying the different from parameters point of view, it is different parameter combinations, but from the inside the function, they are doing the same fittings because those parameters are not taking effect. So what's
Still, will it do all these combinations? Because, the way you are calculating 4 times 2 times 2 times 3 times 2,
yeah.
because for linear, degree will not make any sense. Still, when we say the number of combinations, we still calculate, we multiply all of them.
So let me finish this. So this should be I believe it should be 96, and we are doing the tenfold cross validation. So in total, we are doing 960 times of fitting. So that's why it takes a very long time. So like for let's say back to the question that the degree doesn't apply to the linear kernel. So in that case, we can just split this grid search into multiple phases. Let's say we just find which kernel will be the best kernel, or what is the best parameter combination in linear, what is the best combinations in polynomial, what's the best in radial basic function, and then we compare the best from each kernel.
Yeah, makes sense. Thanks.
Great explanation. Thank you.
So, Professor, one more thing is how do you find out the value of the best parameters? I mean, say for our
Yeah, I will
assignment.
talk, that will be answered in the next few cells. So now we have the best score. So we can see that it is possible to get a well-trained and well-performed SVR model by like setting different hyperparameters. Now the R square is changed from like negative score to like 0.86. That is far better than the linear regression, the best linear regression. So now, then what are the best parameters that can get these values? We can get it through the best primes field. So this is the grid search result for each model. For either linear model or the SVR model, and we call best score to get the best performance score, but we can get the corresponding parameters that generate this score by just calling the best primes. And we can see that in this model, it is using C equals to 5, coefficient equal to 10, degree is 8, gamma is scale, kernel is polynomial. So we can get the best or the optimal hyperparameter values.
But this one is after we ran it. When we are setting the values, how do you know that? Because you can set a lot of other values also. What is the range? How do you select this is the range you have to
What range? You mean
say?
this range?
Yeah, yes. So
You better read the official documentation. It will say that what's the meaning of that and what is by default and what's the meaning that if you increase it to like certain levels and that. So they should be all listed in the official documentations for that. And you can also search for some other blogs for some like experience shared by others. But if without reading those documentation or other informations, of course we don't know like what values we should use, what value range we should search from. Okay. Okay. We get the best model score. We got here. We get the model parameters. We get the model score, and we want to test how the model perform on unseen data, on testing data. So this is the model searched by grid search. And then this is best edge meter. That is the best model in this grid search. And we call it score that we are going to try to use this model to predict the information provided. So now we provide the normalized testing input and the label. So, and the testing label. So now the returned score will be the testing score, will be the model's testing score. So this score is the model performance on testing dataset, and this score is the model performance on training dataset. And we can see that their performance is very similar, and it will it also tell us that it is not either trapped in the underfitting or overfitting problems. It is a like good model fitting. And we can also predict some custom data instead of just feeding the whole testing dataset. So we can just provide some data input, like it should be like five parameters. Sorry, a vector of 5 values, and we try to predict the result by calling the predict method. And we can see that the corresponding price, predicted price, can be returned by this predict method. And the following how we save these models using the Pico library. So we import the Pico library and we give it a name. We just follow this syntax. And these few lines will be used to, just these 3 lines will be used to save the trained model into the file, so that next time we don't need to retrain the model from beginning, and we can just simply load the model from the file, and then the loaded model will be just ready to do the prediction without needing to going through the training phase again from the beginning. That will be very time saving. So that's similar. So we are just saving the trained linear regression model and the SVM model. Okay, that would be for the regression part. I would just quickly, I think I don't need to go through the classification part because the only difference is the dataset difference and the evaluation part is different. So here, the performance of the trained model is not tested using the R squared. It is using the accuracy because it is a classification task. So it is going to measure how many testing cases has been correctly classified instead of like what is the difference between the prediction and the true value. So that's the only difference between regression and classification task. So I will leave this classification notebook for you to play with. Okay. Okay.
Doctor,
Yeah.
sorry. If we get a new data set on this, like, after saving this model, if we get a new data set, like, can we add this data set to the model or? Or do we have to recreate it?
You can train the model from you can retrain the model on the basis of this trained model. So you don't, because initially those model parameters or those model weights were initialized randomly, and it need to go through some iterations to reach this stable condition. And if you acquired new data, you don't need to train the model from beginning, but I still need to go through this training process. But so let's say I think it would be better to draw some.
Wouldn't that be treated as the testing data set and all we should be required to do is just pre-processing? And then pass the data, the pre-processed new data set through the model, through the trained model?
Sorry, let me finish this one. So so this would be our initial training. So we start from the beginning, that is iteration, maybe iteration 0, and the loss is very high. And after we trained the model, the model would reach a stable condition. So we don't need to further train it anymore. Let's say with this current data set, we stop here. And let's say you further collect more data, and now you can just keep training the model from this point using the weight parameter you collect here, and initialize the model using this parameter, and then start training at this point. So you may get something like this, or if the model is already good enough, it may be showing like this. So it depends on the situation, but you still need to go through this like fine tuning or training process. You cannot just there's no way just can update the model directly. So does it make sense? Oh.
Yeah, doctor. Thank you. I understand.
Sorry, what's the last question? I didn't follow.
Yeah, it was same related to what the other question was. I was thinking because, in any real-time scenario, we get data refreshed every day. And I was under an assumption that once we train the model is there, and the new data keep when it comes probably is treated as the testing data, and the model should be able to predict on the should be able to predict on daily basis. But I understand now that it has to go through the entire process every day in that scenario.
Like you don't need to like retrain the model every day. Let's say if you need to train the model or say fine tune the model, you can just reuse the weight parameter values that you already trained and then start from that point. So it will save the time that you used here, right? So you save a lot
Okay.
of time.
Okay.
And and you don't need to do that on a daily basis. Like you only do that when the model performance has been downgraded.
Yeah, but in a data pipeline, we receive incremental data on daily basis, right? So I'm thinking from that perspective. For example, you get some research data, some funding data, which has uh, which should be reflected. So meaning that every day you get some new data set. And I understand where you're saying that, we don't have to retrain, so we can go on till the weight that was used the last time for the new data set. But we will have to send the new data through the system for any of our, for the metric calculations in any reporting requirements.
Yes, but you need to this for this simple models, it's all right if you retrain it frequently, but for some like large or more complicated model, it will take many times to absorb the new information. So yeah, that would be there would be you need to consider that there's some like cost effective matters in that.
Okay.
But
Mm-hmm.
yeah,
I have a question.
there are some models that support like adaptive training, but you may take a look. But for this for model we talk about in this course, if we are providing new data set, we are kind of going through the entire training process again. Like we almost it is almost identical to like retrain the model, but the difference is only we can start from a good start position instead of some random initialized start position. So that's the only difference for all these models we will talk about in this course.
Thank you, Doctor.
I had a question about the that step, the grid search. I press play on my Google Colab and it's just sitting there executing. I was wondering how long it took to do that one there.
For the regression notebook?
Fine-tune parameters for one alarm model. So that run right there. Grid search, see that one. If I hit play.
Oh, okay, grid search. My recommendation is let me see. For grid search, let me find a grid search. So for grid search, I would recommend you add one more parameter. Let's say variables equals to 10, and
Yeah.
it will show you the process.
You could
like
chop out some of the kernels too. Some of those kernels aren't relevant.
Yes, some of the parameters are not taking effect for specific kernels. So you may split the this parameter combinations. But on my laptop, it would take like less than 30 minutes. I haven't run it on the Google Colab. I believe it is slower than mine, but
Oh.
yeah.
I'm so used to clicking run and then waiting a few seconds, moving to the next one. That one.
Yeah,
But
yeah,
I've got a friend, I've got a
it is much
pro.
slower than the linear regression, of course.
Okay.
Then, if you read the docos on the group parameters with the SVR, you'll find you can chop out quite a few of those parameters, and that'll reduce it enormously.
Okay.
May I ask a question about that same one? So are you saying that you should run each kernel separately with the appropriate parameters? So then you would run it 4 times?
So you don't have to do that. I mean, if you let's say this is a lazy way to do the grid search. So we provide all the parameter combinations set here and let the single function grid search to find the optimal values from this. This is a lazy way. So if you want to increase the efficiency or you don't want to wait that much time for this grid search
Yeah,
process,
I
you
tried it
can.
and I think it just timed out. It ran for hours and then it just timed out and didn't give me a result. So
Yeah, yes. In that case, you can just read the document. I say, for example, there are some. Let's say I first want to find the best model that using the linear kernel, and then I specify what are the parameters that is taking effect when the kernel is linear, and I set search in some certain range.
C,
And
epsilon, and gamma are applicable with the kernel of linear. So,
yeah,
quite a few of those aren't worth it.
yeah.
C,
yeah, so
epsilon, and
what
gamma are all you
you're
need for the linear kernel.
Yes,
Yep. So what you're saying is you would run that code multiple times
yes, you
using
can.
one kernel each
Yes,
time.
you can do
Yep.
the grid search for like one kernel each time, and then make a comparison for all these kernels and make the final decision. Because
Okay,
you
so then
already
you would
got
take
the
your
score, right? You already
so you
got
would
the
take your
score
best score from the
from
the
each kernel.
the kernel. So like just say your best score was from the poly, then you would go with the poly.
Yeah, yes.
Okay.
But that's the whole purpose of the grid. It does it for you. And if you read the
Yeah, it's
documentation, it tells you which kernels are worth testing and which parameters are worth testing with which kernels. You can cut your time down enormously.
yeah, but I guess what I'm asking is that you run it multiple times
Yeah, it's okay
with the
to
different
run it multiple
parameters.
times.
Yep.
Yeah.
Cool. Thank you.
Doctor, quick question about the grid search. Some of the kernels like RBF and some of the parameters like gamma coefficient, I don't really understand like from how that impacts the formula or the mathematical formula. Should that be something that we should be looking at, or just like it's just to try it out and see what happens kind of scenario? Like for example, like I don't know like coefficient what it does for which kernel. Like document would say this has an impact on this kernel, but I don't know what exactly is the impact. So should I?
Yeah, you don't need to understand the underlying like equations for this hyperparameters, but there but the but you can try to use your own word to explain the underlying like implication for this different settings for this parameters, like why like setting higher values for this parameter will perform like better performance like that. I think the assignment asks you to give some explanation for that. So you can find some like supporting document or to support that. So try your best to explain the parameters, because that would show the difference for the grading. Yeah, according to the marking criteria. So different level of explanations will affect the grading for the report.
Just thank you, Doctor. On that note, in the past papers, we usually have the breakdown of how many percent is the mark for the code, how many percent for the report. In this particular one, I don't think there's a specific distribution, right? How do
I
you
would
rate?
say most of let's say all the marks will be based on the report, and the code will be used as the supporting materials.
I
So
see. Okay.
so you report some results, and we need to find the evidence on the code, right?
Yep. Okay, cool. Thank you.
That's all right.
So, as a part of for assessment, are we supposed to submit one code file and one report PDF format, right? So one notebook file and one PDF. Is there anything else we need to submit?
That's all. So one PDF report and one notebook file. That would be enough.
Do they have to be in a zipped file?
No.
What do you expect in the report?
So in the report, you need to answer the questions specified in the task. So, and organized in a report format. So it is not like short answer questions, like you list the task and you answer it directly. You just organize it as a document.
But is it like
Is it
but I also put a comment on the code. Is that a report as well? Like
No, for code it's just used for supporting document, and the comments you put on code is just can help us locate the evidence more like efficiently for that.
Because I remember that I read it somewhere, it is 50% code, 50% report. Yeah, and actually we are putting all the comments, like detailed comments in the code, and report has all the observations, all the reasoning behind it, like what as per the task requirement.
So
Because step by step, because in the code file, we explained each step by step with the comment saying what are we doing in each step. And obviously we haven't included that in the report. The report is mostly about as per the task requirement, why did we do that, what are the results that we achieve, and what is the reasoning behind it, why did we choose some hyperparameters.
like for the report, like even when you only want to report like the observation, you still need to describe like what have you done. Then you can
Yeah.
then you get the observation. So
Yeah.
yeah. So we are not expecting to see like the code, the actual code you use in the report. So it's not a like duplication of the notebook file. So, but for report, we still want to see like the procedure that you use. Like you first clean the data set, and what method you use, like what consideration you have. Like did you use the data imputation or you just draw the columns? So we need to know those decisions.
Yeah.
You would
Yeah,
refer to the
that's there.
code.
Yeah.
You would refer to the code from your report.
Okay.
How about referencing? You expect referencing for the report?
Yeah, if you are if you are using external resources or you find some supporting documents, you better just from external resources, you better cite it in the reference. But if you are referring to some like lecture notes or lab contents, you don't need to do that. You don't need to cite it.
So, Professor, code is I'm just copying the same classification one in the lab, this lab, and changing that one to fit the assignment one. So the file will be pretty much similar, isn't it?
You can reuse the code in the lab notebook, and those notebook are just that's the purpose of those notebook. It's used to guide you through the first assignment.
You find most people will do the same.
Yeah, that is the question. So we all will be doing the same. So it's not a problem, isn't it?
I think Turnitin doesn't evaluate the IPython notebook.
It doesn't matter. It won't check the IPython notebook's score. As long as the Turnitin gives a score for the report, it's fine.
Oh, and also, what is the best score for the test R to score? Can you share what we should expect? Is like 9 point something enough, or
There's no such threshold because sometimes it depends on what method. Like sometimes you like people use different cleaning method, and that may affect the final result, but it won't be marked based on your but based on the performance. As long at least the performance should be like sensible, right? You cannot just provide let's say R square with R squares like 0 or negative R square to say this is like good fitting for that. So as long as the result is meaningful or reasonable and you provide some explanation and it's fine. You won't be like marked down if you achieve so there's no like hard threshold for the performance score. Like it is not there is no such threshold saying the performance must
Okay.
be over 80% or whatever. There's no such threshold.
as long my training and tests and is all right, I guess. And
Yes.
as long I prove that
Yes,
there's no
as
overfitting
long
and
as we can
underfitting and stuff like
see
that.
the workflow is reasonable and everything we did is correct and so on. So yeah, if you observe something is strange, like if you think your performance is lower than your expectation or whatsoever, and you have done some like guess or exploration or explanation, you can still like get score for the explanations. Like get more score for explanations.
Okay.
Okay,
Okay, thank you.
all good. Great. Then that would be all for the
Dead on time.
yes, we don't have student consultation time. But thanks for coming and good luck for your
Oh, excuse me, sorry, one more thing. Is that possible if like when you show us the plot where we can see the curve for the training and the tasks and is that possible to do it in this scenario because we have too many variables? Is that possible, or is just taking too long just to see the plot? Because I remember when we did when I did the deep learning, we can have this another software where we can see the line so we can tell whether our model performing?
Yeah, don't worry about that.
Don't worry.
Don't worry
Yeah,
about
but
that
I
at
want
this
I want
stage
to see it
because
actually. I really
yeah,
want
but
to see whether my model is
we
performing.
will see that
Okay,
in later
okay.
course because
Oh, okay,
for
okay.
linear regression and SVM, they're using at least for linear regression, it is using the analytical solution, I believe. So it won't go through those iterative
Okay.
updates
So
of
yeah.
parameters. So there's no such curve.
Okay. Okay. Thank you. Thank you so much.
All
Have
right.
a good evening and thank you so much.
Okay. Good luck for your assignment. And if you have any questions, feel free to email me. Okay.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Have a good weekend.